Hey, hi there. Welcome to today's session. So in today's video, we'll be covering the second part of descriptive statistics. So in the previous session or previous video, we covered measures of central tendency and measures of frequency. In today's video, we'll be covering measures of variation and measures of location. So measures of variation, we'll be studying. In measures of variation, we'll be studying variance, standard deviation, coefficient of variance, all those parameters which basically deal with understanding the spread of the data. And measures of location is very important, guys, because this will be which will enable us to understand the percentile and the quantile ranks of a data, right? So median actually represents the 50 percentile of the data. So although we studied median in measures of central tendency, the 50 percentile concept actually comes from here. Okay, so this is what we'll be studying in this video. So when we say measures of variation data values depend on the method and the source of extraction, and data are broadly classified as population and sample. So basically what I'm trying to say here is data can be treated in a two way. One is population and one is sample. Typically when we talk about, so let's take an example. What is the average price of rice in, let's say, in Bangalore? Okay. What is the average price of rice in Bangalore? If I ask you this question, what will you do? Will you go to each and every shop in Bangalore? Is it possible for you to go to each and every shop in Bangalore and then give me the value? Because either way, if you do not go to every shop, it means that probably you will not come across or you'll come up with a very accurate answer. But going to each and every shop, it will be very difficult. So the each and every shop in Bangalore constitutes the population. And since we cannot go to each and every shop, this is where sample comes in. That is why we do sampling. We extract a sample from the population so that it becomes easier for us to calculate the average price of rice in Bangalore. Let's say you'll go to 100 different shops situated in different locations across Bangalore, east, west, north, south, and then you come with the average price, right? So that becomes your sample mean, the sample average of price. And you obviously take the average, right? Correct? Okay. So if you look at this, we select randomly different points all across the city, and then, but these sample will definitely have some uncertainties because you have not gone to each and every shop. There will be some kind of uncertainties in these different sample points, right? And because of these uncertainties, we need to find out patterns in the data set. Okay, then we'll try to understand how we calculate the patterns and everything in probability distributions. But these sample will help me calculate the average value faster, of course, but at the same time it will have its own uncertainties. And these uncertainties are modeled by or can be explained by standard deviation or variance in my data set. Okay, so typically we talk about standard deviation, we talk about variance, and we also talk about dispersion. So if you look at standard deviation is always in units. Suppose I have the average price of rice, say 50 rupees per kilo. And if I go to 100 shops, I'll get a lot of different prices, right? 50.2 or 65, 70, it will be less value, it will be higher on the higher side as well. And then finally, when we calculate the average, it will be 50 rupees per kilo. Just like mean, we'll have the same unit, rupees per kilo. Same way in standard deviation also, we'll have the same unit. When we calculate standard deviation, it will give me rupees per kilo only. Variance, on the other hand, is actually standard deviation squared. So it will give you the square of the units. Okay, but ultimately it will have units. That's what I'm trying to say here. It will have some unit. These are not unitless quantities. These parameters will have some unit. Whereas dispersion is also one parameter which we use to understand variation, but this does not have a unit because it's a ratio. unlike these two parameters. Okay, that also we'll try to cover in detail using some examples. Now let's try to understand them using examples. So what is the purpose of standard deviation? Right, standard deviation purpose is to find out how the spread of the data is, like how big the spread is or how small the spread is, what is the spread of the data, and how the mean is influenced by this spread. Because if I told you in the previous video, toward the end of the previous video, we saw that when the mean is the highest of the triple M's, right? Mode, median, and mean. The outlier or the higher, there are some high data points on the right hand side. Correct? That is how the mean was influenced. Because ultimately the spread of the data was pretty high on the right hand side. Right. So that is also one purpose of standard deviation. That means that simply looking at the mean, median, mode probably will not help us get a full-fledged idea of the distribution. Parameters of standard deviation and variance will also be very helpful for us to get a complete picture of the standard deviation, of the distribution of the data. And slowly, when we go to probability and statistics, further chapters, you will see, what is the contribution of standard deviation and mean. It's a huge contribution towards identifying patterns in my data set using probability distribution techniques, right? By understanding the probability distribution of the data. Okay. So sample data will bear some kind of uncertainty due to sampling, as I mentioned in the previous slide, because we have not considered all the data points. We have considered some data points randomly, but unknowing or knowingly, there will be some uncertainties inside it. We cannot avoid that. But we also need to evaluate how well our sample represents the population, because the mean value which we have calculated is not from the population. We have calculated it from the sample. But my question was, what is the average price of rice in Bangalore? Not those 100 shops in Bangalore. But you or me have gone to the field, extracted those 100 data points, and has now told me the average price of, rice is this much based on those 100 shops. So those 100 shops better adequately represent the population. It should. Otherwise, your results or the calculation which we have made about the mean will not be accurate. It cannot be exact, of course, but it has to be somewhat within permissible limits. And we have to test our calculation. That is where again inferential statistics will come in, where we do hypothesis testing. But we'll go to that. But before we go there, first let us try to understand some of the nomenclature, some of the symbols which we typically use or which are typically associated with the parameters of any data set. Okay. And please do not forget these parameters, because whenever you read books or articles, these parameters will be used. These are universal parameters, universal notations, I would say. And it's very important for us to at least remember these. Right. So parameter, let's say mean. So if I have mean, my population mean is given by mu. This is a Greek letter, a Greek alphabet, which is called as mu. In sample, however, we denote it by X bar. So the bar is not, I don't know why it is not coming clearly, but it should be X bar. Okay. Standard deviation is given by sigma, which is again a Greek letter, sigma. However, sample standard deviation is given by small s or sigma X bar. But typically we use small s. Okay. For variance is the square of the standard deviation. We all know that. So variance is equal to square of standard deviation and s squared for sample. This is for population. This is for sample. Okay. I'll show you the formula of standard deviation, everything, and variance. But please remember, variance is nothing but the square of the standard deviation. So mu for population, mean, X bar for sample, standard deviation, sigma for population, smallest for sample. Again, variance, sigma square for population, smallest square for sample variance. So if you look at here now, this is the formula, very simple. What does it say? S is equal to sigma of, S is equal to summation of x minus x bar whole square by n minus 1 for sample. And this is for population. If you look at the population, it is fine. But for the sample, you see here, there is an n minus 1 given. You know, why is it so? If you think about it, suppose you have, let's say, two parameters, say k divided by n and k divided by n minus 1. Which value will be higher? The value which will have low value, smaller value in the denominator will be the higher value, right? So k by n minus 1 will be greater than k by n. Typically in sample, since the collected data points is less, the variance or a standard deviation seemingly has to be higher. That this is called as Basel's correction. This actually represents degree of freedom. This is also called as degree of freedom. N minus 1 is called as degree of freedom. In Python, you can separately find out standard deviation for population mean separately, right? np.std or normal.std gives us the population standard deviation, right? And in Python, we have a function.std, and inside it, we have a degree of freedom. If I put it as 1, it will calculate, use n minus 1 to calculate the standard deviation. This is called as degree of freedom factor, right? So this again will come across degree of freedom while doing hypothesis testing. But we'll go to that later on. Okay, so this is what the difference is while calculating standard deviation for population and sample. And that is why the reason we use n minus 1. This is also called as Basel's corrections. Basel's corrections. Okay. Because we ideally want the variance or the sum of squares, actually the sum of squares to be higher for sample than of mean, but not than of population, because in population we have all the data points, right? So the sum of squares may not be that, high, but for sample, we have less number of data points. Sum of squares typically tends to be high. That is what we assume. And this is called as sum of squares, right? When we take the average of sum of squares, that becomes my standard deviation. So standard deviation, you can call it as the average of the sum of squares. Whenever we divide anything by number of data points, we get the average, right? So average divided by sum of squares is nothing but the standard deviation. Sum of squares will also be used in analysis of variance, what we call as ANOVA testing. So all these nomenclature, all these words, please familiarize with it. Please get acquainted with it so that in the next video, it won't seem to you as alien words. Okay, very simple. Sum of squares. What is sum of squares? We're trying to check the deviation of each and every data point here from the mean. That is what the standard deviation is all about, right? Okay. So how do we calculate the standard deviation, right? So if I have, let's say 1, 2, 3, 4, 5, right? Whatever it is. And how do we calculate standard deviation? What is the mean here? First of all, the mean here is 3. 1, 2, 3, 4, 5. The mean is 3. So my standard deviation will be 3 minus 1 whole square plus 3 minus 2 whole square. 3 minus 3 whole square will be 0. 3 minus 4 whole square plus 3 minus 5 whole square. So we're trying to check each and every data point, which we have 1, 2, 3, 4, 5. How is it deviating itself? How is it different from the overall average of my data point? That is called as deviation. And we are scaring it obviously because, values which are lesser than the mean, its deviation will be negative. Values which are higher than the mean, its deviations will be positive. It may cancel each other out. So we're taking a square. And finally, we're taking an average. Finally, we're taking a root over again to negate the square effect, the squaring effect. This is your sample standard deviation. This is your population standard deviation. Its corresponding variance will be just the square of these two values. So it will just be the average of the sum of squares. That's it. So next we have what we call as coefficient of variation. So coefficient of variation, as I mentioned in the second or third slide, where we noted the fact that these are unitless because they are a ratio. So ratio of a standard deviation divided by the mean. Okay. All right. Now, coefficient of variation for sample with this, for population, it will be sigma divided by. So what is variation? Coefficient of variation? It's a relative measure of variability or dispersion. It measures standard deviation with respect to the mean. Basically, what we are trying to do here, we're typically, when we use coefficient of variation, we typically use it. So typically we use coefficient of variation to compare the relative spread of data between two different data sets. And I'll show you how. Let's take an example. Suppose this is my marks x1, this is marks x2. Okay, two different set of marks obtained by two different classes, let's say. So here the marks range from 35 to 96. Here it is from 75 to 89. Great. Now, if you calculate the mean here, the mean here of both these set of marks is exactly same, 75.5 and 75.5, right? However, if you want to calculate, if we further calculate the standard deviation, it comes out to be 24.7 here. It comes out to be 8.7 here. And the number of data points is also same. Right? Here, the mean is the same. So you can easily say that, okay, the variance in case one is higher directly, actually. But if we do calculate the coefficient of variation, we become more confident because coefficient of variation is nothing but the ratio of the S1 divided by 75.5 for this case, and this will be S2 divided by 75.5. So 24.7 divided by 75.5 will be account for 32%, whereas 8.7 divided by 75.5 will be 11.5%. This was easier because the mean was same. So you can see here, although the mean was same, we can have distributions where the standard deviation or the variance captured in both the data sets is different, although the average is same. So the distribution will somewhat look like this. I'll show you. So here we have 75.5 on the x-axis marks, right? And you have two distributions. One where the spread is high for case one. Spread is high, matlab the minimum value is 35 and this is 96. And there is one where it is ranging from 75 to 89. The mean is the same. Mean is the same, but the range captured is different. Spread of the data is different. But there will be some cases where it will be even more difficult. The mean will be different in both the cases and standard deviation also. Then how will you compare? Again, then coefficient of variation also you can use to calculate. This is like it works like a scaling effect because you basically are scaling the standard deviation with respect to the mean of the corresponding data set. Because you might have two different sets of data where the scale is very different. One may be in hundreds, one may be in tens places or units places. But it may be compared to that, the relative variance is found more in your units place. We don't know because it is scaling. We're dividing it back by we're dividing the standard deviation by the mean of the data set. Okay. So next we have measures of location. Now this has got everything to do with the position of certain data points in your data set, which can give you a lot of information about the type of distribution. Right? Is it left skewed, right skewed? Does it have outliers? All these things. Outliers are very extreme values which show a different pattern than the rest of the normal data set. So percentile ranks, quartile ranks, interquartile range, all these things we calculate to understand the location parameters. Now, to do that, first we sort the data in ascending order of magnitude. Okay, always. Then, and these are my 25th percentile, my 50th percentile, and my 75 percentile values. Now, 25 percentile rank, what does it mean? It means it is that data point below which or greater than which 75% of the data is greater than this value. Now, suppose if this value is say 40, let's give an example, 40.1, okay, which means that 75% of these entire data points, suppose we have 1000 data points, 750 values are greater than 40.1 and 250 values will be less than 40.1. That is what it basically means. Again, 50 percentile rank means below means greater than which, because this is an ascending order of magnitude, right? So below which 50 percentile is there, 50% values lies, above which 50% values lies. So this basically is nothing but the median of my data. This is also called as Q1. This is also ranked as Q2. Q3 will be 75 percentile rank, and that will be that value below which 25% of the data will be greater than the 75 percentile rank. Okay, let us take more examples and we can easily understand. Remember the box plot we were trying to evaluate in visualization. Box plot shows these three values: 25 percentile, 50 percentile, 75 percentile, minimum value, maximum value as well. Okay, it also shows the outliers actually. So this is the box plot, right? Okay, so you can see here the lowest value, the highest value, Q1, Q2, and Q3. So this Q1 is nothing but 25th percentile. This is the 50 percentile or the median. This is also 75 percentile. Now, what's the difference between percentile and quartile? Same thing, just that typically 25, 50, and 75 are called as quartiles. Okay, whereas percentile can be anything. It can be 99 percentile, it can be 1 percentile. All other values are typically called as percentile. So basically, your all quartiles are also percentiles, but all percentiles are not quartiles. So you can call it as percentile or quartile. It's up to you. In Python, we call them as percentile. We have a function, in fact, np.percentile. So to calculate percentile value, we directly use the percentile function. So you can call them as percentiles only directly, instead of calling them as quartiles or quantiles. Okay. Okay. So measures of location. Now, how do I calculate it again, right? Please understand again, these formulas are not important, guys. I'm just showing you so that you can relate it to your college and school work. But in Python, we have inbuilt functions which we can use to easily calculate the quartile or the percentile values. Now, if you look at this data point, these are the scores, and this is the same set of data which we had used before in the previous video, I guess. So you'll be able to relate to it more. Okay, it's the same data set. So now if I want to calculate the Q1, Q2, Q3 values, how will I calculate? Okay, so your Q1, so I stands for 1, so this I will become 1. Okay, so this will be equal to 1 into total n is how much? Total n, for that we need to calculate the frequency or cumulative frequency. You want to calculate number of data points. If I remember, it was 35 if I'm not wrong, right? So now if I have to calculate the Q2, so the Q2 will be this, I will become 2 into n plus 1, 35 is the total number of data points. So 36, 35 plus 1 is 36, therefore, so 4, 9, 2 9s are 18. So Q2 will be 2 into 9, Q3 will be 3 into 9, 27. So this is the 18th value is my median of 50 percentile. 27th value is Q3. So this is how we can easily find it. Okay, please understand here the median, using this way method of finding out the percentile value, using the percentile value to calculate the median will always be a value from the data set, right? Correct. Whereas when we calculate the median using some formula for group data points, it was, I think, coming out to be 107 or something, right? Some difference is here because the methodology is different. That is why I was telling you, don't need to remember any formula. Whatever programming language Python will give us, we'll take that and move with it. Typically, use this logic to find out the median. Okay? Please don't get confused. Statisticians over the years have come up with different methodologies to calculate the same parameter. At that time, there was no programming language. They had to do it manually. Whatever suited them best, they have to use it. But now we have programming languages. We don't need to remember any formulas. But yes, if the median is greater than the mean, how does my distribution look like? Those things you should obviously need to understand. You have to remember. So now, when you try to find out the interquartile range, this is called as interquartile range, IQR. This is the difference between the 75th percentile value and the 50th percentile value, which is 123 minus 80. And this value is 43. So the approximately 20 on each side of Q2. Q2 is the median. Approximately 20, एक में 20, कहीं पे 23 होगा, no problem. If there is skewness, there will be unequal distribution on either side of the median. Because if it's symmetrical, the median, the mean, the mode will be same. So IP also can tell you how the data is spread. Now, if you look at this, right? 80 on this side, 120 on this side. IQR is 43, right? IQR is basically 43. So evenly to distribute nahi hoga ye, hai na? Because 2 is 217. So probably some kind of right skewness may be there. We don't know. Understand can be plotted, right? So plotting is the best way to deal with it, and it can be easily done with one single line of statement in Python. So finally, what did we learn today, right? So first, what we learned today is that if you want to understand or draw inferences from a data point, from a population, why do we draw inferences? We draw inferences so that we can make a generalized statement. The average price of rice in Bangalore is actually 50 point something rupees per kilo. But can I directly go to the population? No, I have to draw some random data points, random selection, randomly I have to select some data points, create a sample, and from a sample, we'll calculate the parameters, right? Like mean, standard deviation, proportion, coefficient of variation, whatever it is. And these parameters are actually called as sample statistic. So statistic is that value which we calculate from a sample, right? And from these samples, sample values or sample statistics will draw inferences to comment on the population parameters. So those mean, median, or whatever proportion or whatever it is, those entities which we calculate are called as statistic for sample in case of sample, and the same entities are also called as parameters for the in case of population. So population mean is given by mu, and population sample mean is given by x bar. So x bar is called a statistic, mu is called as a parameter. So please be very careful. I know we loosely use the word, no problem, but these notations have to be appropriate, guys. You cannot afford to write x bar to denote population. Please don't make the mistake. Statistic parameter, okay, you can, it's fine, forget, right? But notation should be correct. When we draw these inferences to comment on this, right? That is how we do it. But someone may argue why the long road, why couldn't you have directly calculate the population, use the population to calculate these parameters? But it would take a humongous amount of effort and time, right? Is it possible to go to each and collect each and every data point from population? No, it's impossible. Population is the universe of those data points, right? And because of that, we use this flow. So since the calculation of parameters directly from the population is not feasible, we do not use this approach. Instead, we use sampling to draw inferences from the population. When you draw these, or when we calculate the statistics from a sample, we use those statistical calculations to draw inferences from the population indirectly. But we don't do it directly from the population parameters because we do not have the population data. It's not possible for me to, store my population data. It would require a huge amount of time and effort. This is where we end the descriptive part of statistics. And the next video will start off by understanding the basic concepts of probability, and then we'll move on to probability distributions. See you in the next video.